this morning then with Brendon, we did a lot of useful thinking about probability theory, the basics of where Bayesian data analysis comes from. And so now we're going to switch gears, go to a IPython notebook and try and do some moderately practical inference. You'll see that it's not terribly practical, but we'll talk about that as we go. And apologies in advance for the quality of my Python. I'm embracing my imposter syndrome here and just putting up my terrible NumPy for everyone to see. And hopefully you can help me make the notebook better over time as you see the things that are wrong. So don't laugh too loudly. OK, so what are we going to do in this session? My goals for you are that by the end of this, you'll be able to set up and carry out a simple Bayesian inference, which is to say characterizing a simple posterior PDF for some parameters given some data. We're going to compare brute force analytic and MCMC sampled results. We're going to do some model checking with the posterior predictive distribution that Brendon showed right at the end while you were all thinking about coffee. So we'll go through that again. And then we're going to look at the Bayesian evidence in a little more detail and how it can be used to compare various models and spend some time trying to understand its properties, which is important. And along the way, I'm going to suggest some simple hacks for those of you who want to get some practice with Bayesian inference. OK, so let's go. We'll work our way through the usual setup and get down to some sort of statement of our problem. So imagine we have a data set. We're going to make it ourselves, but it's going to be observations of some observable y with reported uncertainty sigma y at given x values. Yep, John. I'd postpone that for now. You're not going to actually need it in this lecture. When we get to that point, I'm just going to show you the image and we'll fix that bug later. OK, so this is actually the same problem that we went through on the board on Tuesday, but I know that not everyone was watching the board in the breakout, so we'll go through it again. OK, so we generate some data and make this plot. So this is the first test of whether you're following along. OK, so there we go. Some data points, somewhat plausibly drawn from some kind of linear-ish relation. So observable y on the y-axis and observable x on the x-axis. Didn't work for Rutger, but hopefully it'll work for others.
Comment that one.
I see. OK, so the fix was to comment out import daft in the straight line utils. Alternatively, you could do, let's see, you could do this, pip install ---- upgrade daft. Which will take a bit longer. So this afternoon, I guess we might have a breakout on how to install packages that just work like that. If Daniel's around, I think he offered to do something like that. So hopefully you should be able to get to the point where you can see this, a picture like this. It did, yeah, because I generated a new data set from the sampling distribution. So I got a new noise realization. So hopefully, when we've sort of figured out the daft problem, the first hurdle, everyone will look at a slightly different realization of the data, so we can do some completely unrealistic comparisons between alternative universes where we had different data sets to work with. OK, shall I continue, or are you all still pip installing daft with this line? On the upside, once you have pip installed daft, you'll have a really good package for drawing probabilistic graphical models.
Could you just take a second to list some examples of how this is very commonly used?
How what is commonly used?
Just, the X versus Y, like astrophysical examples of when we would do this. When do we see this in papers, or when we put it in our own papers?
Yeah, so examples of when you see this kind of plot. I guess in astronomy it's very, very common. So you see plots like this all the time, where there are noisy measurements, y, given relatively well-known positions, x. So for example, measured periods of Cepheid variable light curves for Cepheid stars of different magnitudes. And you see an approximately linear relation between the two. Yeah.
We have a complaint from the internet that your cell phone is interfering with the transmitter. I think we just run it.
Yeah. Thank you. Thank you, internet. Okay, so I'm going to carry on and hope that at least one of you on each table is able to generate a data set. Who's looking at their own data set plotted? Good. Well done. Thank you, Daniel, for making a package that just works. Okay, so the first thing we might do with a data set that looked like this is you might remember people talking about fitting, and so you might think, oh, I'll try and fit a straight line to this data set. So here's the industry or an industry standard, a least squares straight line fit. And what you're doing in that procedure is to find the straight line that goes through all those points and in fact minimizes the mean square residual between the line and each data point. Right, so it's a reasonable algorithm for finding a straight line that goes through those points. And so you write down an equation for the straight line, y equals mx plus b, and then write down this mean square residual, and you might weight it by the uncertainty to try and take that into account, and you end up with this summary statistic called chi-squared, which we might have seen before. And if you want to minimize that with respect to m and b to find the right gradient and slope so that the line goes through the points, then you differentiate chi-squared with respect to m and b, and then you'd end up with a linear equation between the parameters m and b and the y, and you can package those into vectors and then solve it with linear algebra, and that's what this NumPy package linalg.leastsquares is doing. So we're going to go ahead and just do that without thinking about it anymore. So here we go. This was setting up some arrays that you need, and then what's that? You'd publish that fit? Very good. In a computer science journal. Oh, I didn't say that. In AppJ. Okay, good. So there's our least squares fit. So now let's spend some time thinking about Brendon's solution to the same problem. Right, the problem was, what are the values of the intercept and gradient of a straight line model for the above data? And Brendon's answer, the Bayesian answer, would be not a best fit line, but the posterior probability distribution for the parameters m and b. So the answer isn't going to be two numbers, it's going to be a distribution that we can plot. Yeah, Kelly.
So I know that the chi-squared isn't Bayesian. Is it frequentist?
It's a summary statistic. So the question for everyone out there was, is chi-squared frequentist or is it Bayesian? And I think my answer is about to be that it's both. It's a summary of the data that includes two parameters. And it's used by people in both camps because it clearly makes sense.
Okay.
So it's the mean squared residual between the prediction from a model and the data. So it's something sensible to define as a summary statistic. And it turns out to have a Bayesian interpretation, which is the thing we're going to talk about. Okay, so we're after this posterior PDF for the parameters given the data. And so let's derive this posterior PDF so that we can calculate it. So we're not looking things up in recipe books here. We're deriving from all the first principles that Brendon showed you what to do with actual data. So let's spend some time doing that. So the first thing we do, or at least it's sometimes often helpful to do, is illustrate the model that we're trying to fit. So the illustration of choice is a probabilistic graphical model. And for those of you who were there on Tuesday, you'll have seen this before. So what you can think of this as is a recipe for generating data, or if you like, for simulating mock data that is like our real data. Because when we do a fit, we're trying to find a model that predict data that are like our own, that fit our own. That's what to do a fit means. So we have M and B, which are parameters of our model. And if once we've chosen M and B, a gradient in a straight line, then we can go to each one of our X values, which I've omitted to draw on this diagram, apologies. We can go to each one of our X values and predict the Y value, this YK true. So if we know what X is, and we know what M is, and we know what B is, then the straight line equation tells us what the true value of Y is. And if we know what the true value of Y is, then we can simulate what the measured value of Y is, the observed value of Y is, by adding some noise. So draw a Gaussian random number or something, and add it to the true Y to get the YK over the right-hand side. So the two circles around YK is to remind us that YK is things that we've observed. They're constants handed to us in a file, or in our case, being spat out by a generate function that I wrote for us.
Sorry, can I go back a bit to the chi-squared? I think this has caused a lot of confusion. I wouldn't call that chi-squared. I would just call it x squared or something. It's a sum of squares. And it distributes a chi-squared under certain conditions, right?
So the question was, is it confusing to call this summary statistic chi-squared? And someone at the front suggests that it is because it has serious implications for some statisticians. I think that's a fair comment.
Yeah, I think I've seen this confusion many times. I mean, you just call it a sum of squares around the model.
Yeah, and in fact, yesterday in the machine learning lecture, they did call it something different.
Yeah, and then, you know, there's certain conditions that will distribute as a chi-squared.
Ah,
because
so
for a statistician, chi-squared is the name of the distribution, not of a statistic.
Right.
And that's one of the things that causes the confusion. When I talk to statisticians, I lose them when I talk about chi-squared.
Right, okay, good. So it was pointed out here that for a statistician, chi-squared is the name of a distribution and not for a summary statistic. So this is loose astronomy terminology. I apologize for that.
Yeah,
but
I'm not a statistician, but it caused lots of confusion when I learned these things, that because there is a distribution that is very well known. And
Yeah.
that thing will distribute as a chi-squared
Yeah.
if there's a Gaussian independent.
So I'm not a statistician, but I play one of the department. Everyone would be happy to call it the sum of squared residuals.
Yeah,
But
the
I
weighted
don't-
sum of square residuals.
Weighted
Yeah.
sum of squared residuals, or standardized sum of squared standardized residuals. But I don't know what symbol they'll use for it.
I guess it varies from practitioner to practitioner.
Yeah.
Yeah, I mean, experts sounds.
We are, but one of the points of AstroHackWeek
I see.
is to make it easier for astronomers to interact with data scientists in other areas. So,
All right, I'm going to call it capital W. How do you like that?
Statisticians don't have a symbol for that name.
The problem is then you could do then the usual strategy would do a test. You would say, are the residuals too big? And then you could do a chi-squared test. But then the thing does not need to distribute like a chi-squared unless the assumption.
Right.
But I feel like even in, what is that book that has the train, I feel like in our, you know what I'm talking about?
yeah. Because physicists use it that way. Another thing you could call it is the metric distance. It's like the squared metric distance.
The squared metric distance is another name for it. And I guess then we choose a symbol that emoted metric
like
distance. Delta S squared.
Like that's how a geometer might think of it.
Okay. I'm not going to change the symbol again. I like
When
W.
you change it to W there, did it change everywhere in your whole Jupyter notebook?
No, at times I guess I continue to call it chi-squared. So, but spelt CHISQ. So I guess I could have done that as well. All right, let's move on.
Pronounce it
Chisk.
That's a good idea.
Okay. I bet everyone out there on Twitter is really wishing they were in the room right now. If only we were there, we'd take part. Okay, so this PGM that I showed you, you can think of it. It's useful to think of it as oh, yep.
About that.
Mm.
Did you choose not to put the XK, or did you forget?
I forgot to put the XK in. Sorry about that. So, quick question for the people out there who remember Tuesday. Where does the XK go in the PGM that I've drawn badly? It helps if you can see the bottom of the box. So xk, there's one for each data point, so it has to go inside the plate. And it's handed to us as a constant, right? If you remember the data up here, there were no error bars on the x-axis. So the x's are given, they're part of the design of the experiment. And constants appear in this recipe as colored in dots. So it would be a black dot labeled xk with an arrow pointing to y true k, because we need that in the straight line equation. So to simulate data here, we would think of an m, think of a b, use the xk for each data point to generate a y true k. Deterministically, that's why it's a dot for y true. And then given those y trues, we would then draw a value for the observed yk by generating a random number. So the circles indicate random number generators, probability distributions that we draw from. And in order to do that, we need a sigma k to tell us how wide the distribution is, and that's handed to us as well as a constant. So this is a recipe for making simulated data. And the nodes in this graph represent probability distributions that we have to assign, except for the dots, which we already assign, they're delta functions. Right? If you draw a parameter from a delta function, you just get the same number every time. Right? So think of the dot as a delta function probability distribution, and the way to remember it is you're seeing that probability distribution from above. Right? It's a delta function which looks like a dot from above. Okay, so this is recipe for the forward model, and it's a forward model that includes drawing an m and a b from some probability distribution. So this is the general forward model for any straight line data set.
What uses the box?
What uses the box? The box reminds us that we're doing this for a set of data points k. And the reason it's in having the box is saying that our data points are independent and they can be treated as in their own box where there are capital K of them. And in each one of those layers we're make a true y and then simulate an observed y. So yeah, the box implies independence of the yks. Okay, so this was for the forward model. We can also use it later, but let's have a look. So I'm writing here that it's a complete description of this forward problem. And in fact, that process that I described of generating mock data by drawing random numbers from distributions allows us to draw everything that was in a circle, or anything that was in a probability distribution there, from a random number generator, which is to say that we're drawing from the joint PDF for all of the variables in our problem. So you saw this morning what joint PDFs look like. So I've written out the joint PDF here for M and B and all the observed YKs and all the true YKs given XKs and sigma Ks that we're handed on a plate and something called H1. And what that box implies, and you can't see it because of the shoot. You can almost see all of it. What that box implies is a factorization. So going from the top of the diagram simulating data forwards is the same as going from the right-hand side of this right-hand side. So first we draw an M and a B from that prior distribution over there. That gives us our true M and true B. And then given that, we can generate yk. So there's P of yk true given an xk and an M and a B. And then moving in, once we've got the y true, we can draw a yk for a noisy observed yk. And then the product sign is encapsulating this independence of data points. Because that product, if you imagine expanding it out, you'd have P of y1 given y1 true multiplied by P of y2 given y true 2 multiplied by, and so on. So, on your table, talk to your neighbors for about 5 minutes about these questions, which I will read out for you now, and then note down some brief answers if you want, and then be prepared to provide them back to me when we come back. So, where did the product come from? What assumption does it encode? Why are the xk and sigma k always on the right-hand side of the bar, but yk is sometimes on the left? What's the meaning of h1? What functional form does the conditional PDF p of y true have? What functional form do you think we should assume for the sampling distribution, that is the probability of the data yk given the parameters? And then what functional form should we assume for p of m and b? So have a think about those on your table for about 5 minutes. You will need to talk to each other. Where's my, I can't time with my, I guess I can time over here as long as I don't interfere with the microphone.
Yeah, I think it's just
there we go. And the duck of doom will call us back after 5 minutes. And it broke everything?
But my notebook did not look like your notebook.
I had to delete and refound.
Yeah, git pull.
I did git patch it.
Oh, I see. If you fetch and then git patch and git merge
All right, but do talk about the questions just to remember what's going on. I guess actually you guys are probably all experienced Bayes users, right? You're not so experienced?
my first time.
Ah, okay. So it's important for you that the rest of your table talk to you about the questions in the exercise.
I will make them talk.
Good.
Yeah, I committed
So the fastest thing to do when in the middle of a lesson is just to make a fresh clone and then fix problems as they come up.
I've done that a bunch of times, but I'm losing what I saved every time. I've done it like 4 times already.
Oh, because of merging in on top of things?
I don't know, just like my fork seems to break over and over. And
so I mean a fresh clone of the base repository. But that's only when in a lesson, because the best thing to do right now is to think about these questions together. So here they are. You should come pair code with John and talk to John. Yeah, and I'm sorry about the notebook confusion. That's bad. Who are you talking to about questions, Doug? Or you're skipping? That's okay. Ah, good. You're going to pitch it after lunch, right? There'll be some time to pitch things if.
I'm happy to pitch.
If it's not a project that's already ongoing, or is it?
Well, so Alex is usually
Which you could also model
Could be good. Yeah, it's a good one for after today, right? You could pitch it as an opportunity to immerse yourself in. Oh, I can't hear the duck from over here, can I? Can't hear the duck from over here. I feel really bad, like the notebooks, it's a distraction because people are trying to fix Git problems when they should be doing. I'm annoyed about that. Well, because there's this bug that meant that they couldn't run everyone had to fix the bug before you could go on. And now they're hitting the same problem over and over again, which is they want to make notes in the notebook. But then they can't pull in the latest version because it interferes with their edits. So next time I have to write here's how to deal with Git during the workshop, because it's a total distraction for people who should be thinking about problems. So that's my bad. I got to fix that for next time. So the fastest thing to do, to tell them, the fastest thing to do is make a fresh clone of the base repository. So just pull directly from AstroHackWeek and just start making notes anew and deal with it later. And then there'll be a horrible merging process for people, but the quality time is talking to each other now about statistics. Yeah,
Is there any way to show the questions and questions around?
Well, everyone should have the questions in front of them, so like that, okay? Yeah, that is better, thank you.
I managed to activate the microphone on the camera,
Mm-hmm.
and I'm going to see how people understand the questions on the live stream.
Yeah, so at the moment I'm repeating back. Is that the right thing?
Yeah, no, at the moment that's the right thing. But maybe when I tell you to stop, this is where I have to look things. I'm not actually, I'm not
The other use. No, okay. I think we'll hear the duck of destiny from over here, but we will have to turn it off. So.
Yeah, because there's a lot of discussion going on, and you know, it doesn't make sense.
Yeah. So this is another thing I got to learn. Is like provision of room microphones is becoming like essential. I just have to remember like every time I do a meeting, I've got to get room microphones. I have this problem over and over and over again, and I keep forgetting to solve it. No, but I knew that we needed room microphones. All right, the duck of destiny is calling us back to the front. Let me turn off the duck, lest he interfere with the internet. Okay, so all of you should have at least some answers to some of these questions. So feel free to stick your hand up and contribute. Where did the product in this factorization come from? What assumption does it encode? Real quick, I already told you this. What assumption is being encoded by the product, Rutger?
It is the identical.
Right, that the data are independently and identically distributed. Yeah, exactly.
Well, as you have it here, it's only independent. And that PR could be.
That's true. It's not identical, just independent, because we haven't specified the functional form for any of the PRs yet. Thank you. That's good.
And the sigmas are different, so I don't think it's
Not quite identical. Okay, good. So just independence, not identical. I really wanted to use this fancy term IID, but I guess I can't.
No, we never use that.
We never use that. Yeah. Okay, let's keep.
Brendon had another comment in here, which is that the fact that you're doing that product means that you are modeling the conjunction of all the y's.
Fundamentally, the product is from the product rule, because your data is that y1 equals 1.3 and y2 equals 1.75 and y2.
Good. So it's encoding the product rule for probabilities.
Yes.
And because there aren't any conditional dependencies between yk and yk plus 1 or y other k, we can write it as a simple product like this. All right, thank you. Okay, so why are the xk's and the sigma k's always on the right-hand side of the bar?
Sorry, can you say that one more time?
Why are the xk's and the sigma k's always on the right-hand side of the bar in this expression? What does it mean to be on the right-hand side of the bar?
Given.
Exactly, they are given to us.
We decided them.
We decided them. We designed the experiment so that they would be fixed constants, which we then just go ahead and use. Right. So they're always given xk and sigma. But the yk is sometimes on the left, sometimes on the right. What does that mean about yk? John?
Look, I understand why xk is a given. I don't quite understand why sigma k is given.
Or it was estimated in an independent fashion.
Okay.
Yeah, I guess at some level I'm choosing sigma k and xk to be on the right-hand side of the bar. I'm saying I did that one line generate data and then I made a plot. But then between then and here, I made some additional assumptions, which is I'm going to treat the xk's as given and I'm going to treat the sigma k's as given.
Well, I guess the xk's are given because they're the things that you measure. They're the values that you measure at.
They're the values that we measure yk at, yeah.
But so I guess the sigma k's are given because you
Instrument like errors.
Because you just decided that your uncertainty is going to be 10% or 20%.
You think you know your uncertainty, you can estimate it independent of this thing.
Yeah.
But if you've estimated them, and technically I think up on the probabilistic graphical model, they should be in a double circle.
Okay.
Then they're observed.
Good. So what's the difference between observed and observed things and things that we're going to treat as constants? So things that we're going to treat as constants, we put in dots and we just treat them as constants and never worry about them. Things that are in double circles, we call observed, and we worry about what might have been. Right? So there's some uncertainty in the data, which is to say we think if we'd run the experiment again, we would have been able to do it in an alternative universe, we would have got different yk. things could have been different. And that uncertainty is encoded in the PDF for YK. It's called the sampling distribution. So we have a sample of data, and we understand that that sample could have been different. But with the sigma k written as a dot here, we're saying that those sigma k's could not have been different. We're going to assume them to be constant no matter how many times we do the experiment. So it's a pretty strong assumption, but we're going to go ahead and do it anyway.
And it may not be true. It is a simplification that we are choosing to make.
Exactly, it's an assumption. So we have to write it down along with our long list of assumptions. That I guess that's always section 2.2 or something in the paper, right? Where we have method and then assumptions of our model.
But I think one of the reasons to be a Bayesian is that it forces you to write down your assumptions very clearly. There's kind of a procedure you go through like this in which you write down your assumptions.
Yeah, it forces us to write down our assumptions, that's right. So every time we do an inference in Bayesian statistics, we get together in a big room like this and we spend a long time looking at a whiteboard with a probable graphical model on it and writing down assumptions.
That's not really true.
Is that not really true? I don't know. Hog and I have spent many hours doing exactly that.
And then once you've still in the prior, then the smoke comes out different color.
Sorry, what was the question? Does it come out in the paper?
I think it does.
In our papers, we try and make it come out in the paper, that we make these assumptions. And I try and write it in the abstract, that given these assumptions, these are my conclusions. Otherwise, people might get the wrong idea. They might think that I've made a bunch of different assumptions and compared them against each other.
I almost feel like we should do a breakout on writing a paper that contains a Bayesian inference. Because I have very strong view that you should open by listing all your assumptions. Then you get your answers conditional on your assumptions, and then you discuss by going through the assumptions and saying how are they affecting your answer and what would have been different if you'd done different, assumed different.
Make it a LaTeX template.
It could be like it could almost be a template.
Good. So there's a hack suggestion here for the people who can't hear the discussion, which is that we could make a LaTeX template for a paper, which guides you through how to write the report of a Bayesian analysis, and it would include a section on assumptions and then the corresponding discussion of them later. Andrew.
We also discussed how to break out of the prisoner's dilemma of getting people to stop writing abstracts that sound like they just proved something. That was assumption. I mean, right? I mean.
So that was a little diversion into the game theory of competing in academia and how you should write abstracts.
Well, yeah, it could be tied to our session on getting a job, our breakout on getting a job.
Right. So my approach to winning prisoner's dilemma is just do the right thing and hopefully everyone else will join in and become a good actor. Okay, all right, enough of that, enough.
Furlough right now.
There's also the peer review process. We actually do have a lot of influence on the way this is done. If you're refereeing a paper that doesn't say what their priors are, you have the power to put that in your comment and say, look, there's this LaTeX template.
Good. How much more powerful would your referee report be if you could point people to the URL of the Bayesian analysis LaTeX template?
Out of our control. That's why we have peer review.
All right. So this is turning into a possible actual thing that might get done this afternoon. Okay. What is the meaning of H1? Anyone suggest what H1 mean or remember what H1 means? In this context, it's always on the right-hand side of the bar. It doesn't appear in the graphical model. It was in Brendon's lecture this morning. It's the hypothesis, right? It's the list of assumptions. It's all of our background information.
So it's basically the graphical model.
Except there's more to it than just the graphical model. The graphical model captures lots of it, as much of it as possible. But yeah.
For example, is it the functional expressions for the sampling distribution? Is it there?
Exactly. So that's why the PGM is not quite complete, because we've just drawn circles. We haven't assigned functional forms. The H includes the functional forms we assume. Okay, so talking of functional forms, what functional form does the conditional P of y true given x, m, and b have? I told you this as well. It's a delta function, because it's a deterministic relation between given x and implied y for the straight line model. What functional form do you think we should assume for the sampling distribution or distributions? So P of observed y given true y. What would you do if you were generating mock data? What would you assume for that distribution? What random number generator would you use to make mock data?
It depends on what y it is.
if it's a spectrum, so maybe Poisson distribution, if it's height in the height of people, so it's big Gaussian?
Good. It's context dependent. You have to understand something about your experiment in order to assign a sensible form for this.
Do you think you could put the answers to these questions in the notebook later? Because it's really hard to get back here right now.
Yeah.
Use the mic?
So I'm trying to use this mic, but I guess it's not working so well. If you can't hear at the back because of the rustling, take a few minutes now to move forward. And also at the end, I will write the answers into the notebook. So while I will just avert my gaze while you reconfigure yourselves. But so the functional form for the sampling distribution is context dependent. In this context, all we're told is a point with an error bar. So what's a sensible assumption? What would you do in practice? Yeah, use a Gaussian?
Because you know the error.
Because you know the error bar. Yeah, it turns out that if you know a point and its uncertainty, the least committal thing you can do is assume a Gaussian. So that's a whole other story, but if you want to learn more about that, you should look up the principle of maximum entropy. Okay, so Gaussian seems pretty sensible, and you were probably all thinking it. What functional form should we assume for P of M and B in this problem? Suggestions? It's a very personal question, this, sorry. But let's probe your inner prejudices. What should we assume for P of M and B?
Uniform on B.
Uniform on B? Okay, over what range, Sora? You want to see the data again?
Minus infinity to infinity.
Minus infinity to infinity. Okay, that's adventurous. Doug?
Uniform on B is very scary because all of the values will be nearly vertical.
Okay, uniform on M, the gradient is very scary because it implies... Right, because it implies a large number of very steep lines. So uniform on gradient seems like a bad idea.
I like uniform on B though because I like translational symmetry.
Right, okay, so Brendon likes translational symmetry, moving these points up and down. So, but Kelly, how do you feel about uniform prior at the moment?
It depends on the order of magnitude.
Right, it depends on the order of magnitude. So do you know the order of magnitude of the intercept here? It's going to be around 100, right?
Oh, yeah.
Ish?
Without taking into account the Y. Before you had seen the Y.
I feel like you're conditioned on the data.
Before I had seen the Y values, no, I probably had an idea. If I'm measuring the period or something of CVs, that was the example, then I'm not expecting it to be 1,000 days. Well, whatever, I'm not a CV astronomer. 1,000 days, I'm expecting it to be 100 days. I also know the time period over which I took the data, so I couldn't even be sensitive to 1,000 days.
Good. Okay, this is an excellent thing being said by Kelly here, which is that she imagines having some prior knowledge, expert prior knowledge of B in advance of seeing the data, because there was a frisson of nervousness around the room when we started looking at the data and assigning priors for it. But you have to live. But no, it is true that in practice you would have seen something like this before. And so you may well know the order of magnitude for the intercept, and so uniform in intercept makes some sense because of that.
Uniform in linear space.
Uniform in the parameter intercept, yeah.
But uniform linear, not uniform.
Uniform in the parameter intercept rather than uniform in the log of the intercept. Yeah. Okay. That was good. All questions answered. So now we can code.
We didn't do the prior on M.
Sorry?
So that was just B.
So I was asking you personal questions about what would you assign for M, and Doug said he didn't like the uniform on M, so maybe he would do something else. But I didn't probe too much because, difficult. And now I'm going to show you my personal prior for M in a minute. Okay, so we now have to do the inverse problem. No, that was the forward problem. So now we have to do the rearrangement that Brendon showed us this morning. And he showed it in terms of Bayes' theorem, which made it look very simple. I'm going to make it look difficult, just to test your following of probability expressions. Okay, so that factorization above was the forward problem. It was the right-hand side there. So we took, if you look at the left-hand side now, that's the joint probability for all the variables, M and B, and the observed Y, and the true Y. So we did one factorization on the right to do the forward problem. Now, when thinking about the inverse problem, we've got to remember what we're actually trying to do here. A long time ago, we started talking about trying to infer the gradient and intercept, which is to say what we want is P of M and B given observed yk. So we have to get the yk's onto the right-hand side of the bar. So that tells us what factorization we need to do. So look at the middle thing here. Let's see. I may have written this in the wrong order. Okay, so this section in the middle, if we factorize the left-hand side, then you see we've got... I did have it right. Top cell first. Okay. So we know we're going to need to get to something that looks like P of M and B given yk. We also know one other thing is, which was we need to get rid of all these true yk's. They're in the way. We're not interested in the true value of y. We're interested in the data and the parameters. So which is to say we have to marginalize over the true yk's. And so there's an integral here over all the yk's. And so this is just writing out that same factorization, but with the right-hand side being integrated. And the left-hand side, I've done the integral as well because you can see the yk trues don't appear anymore. So that's good. And then because this P of y true k is a delta function, we can just go ahead and do this integral, despite its huge dimensionality, and replace the y true k everywhere with just mx plus b. Okay, so now it's starting to look a bit more manageable. And now we need to do the factorization on the left. So we need to get yk on the right-hand side of the bar. And so we do the rearrangement that Brendon showed this morning. And we end up with this thing here. So you see now the factorization has the prior separated P of M and B given H. And then next to it we have P of yk given M and B. And the product of those two things gives us the joint distribution for P of M and B and yk. So rearranged, we get Bayes' theorem again. Okay, so I packaged up some stuff here. This Z is shorthand for P of the data given the model. So that appeared this morning. That's this evidence factor, the evidence for model H1. And it also goes by the name fully marginalized likelihood, as you heard, because it's a big integral over all of the parameters. Okay, so this is the thing that we're going to compute later, and the posterior PDF here, P of M and B given data, is the thing that we want to evaluate. That's the answer to our problem. It tells us about all plausible values of the gradient and intercept given the data and our assumptions. It's the answer to a Bayesian.
I have a question.
Yep.
At the top, you write that you're absorbing xk and sigma k into H1.
Oh yes, I did say that. Yep. I'm absorbing xk and sigma k into H1. Yep.
And yet in some of the givens you have sigma k and H1 separately.
Yep. That is, yeah. That's a typo that I have
so
sigma k's and hk.
I'm thinking correctly that it's pretty much you putting it all into H1.
Yeah, and you know you're thinking correctly because you spotted that error. So we should fix that in the notebook. But yeah, those should have been absorbed into H1. But I guess I found it useful to keep the xk at least hanging around so that I could write mx plus b. So I should reword this somehow so that it makes more sense. Yeah, at the back.
Could you repeat what the error was?
Oh, the typographical error I made was that I first said I'm going to absorb xk and sigma k into H, and then I didn't do that.
Well, you did on the left-hand side.
Yeah, that's true. I did it on the left-hand side, but not on the right-hand side. This is pretty sloppy. We should tighten this up, don't you think? We should make this notebook better. Okay. Yep.
This is maybe going to sound flippant, but do you really do this every time you're doing something like this for a paper? Because this looks like, for a problem that isn't this, it would be very hard.
So the question is, do we really always do this for a paper? In practice, there are shortcuts that we take because we've seen these things before. But the reason I'm going through it in this level of excruciating detail is because when you get to more complex problems that involve parameters and hyperparameters, it's really helpful to go through this, because you really need to keep track of all the assumptions that are involved in each step. So it's this kind of Bayesian reasoning is a sort of double-edged sword. On the one hand, you have to do all this derivation work. But on the other hand, you get to do all this derivation work, right? Because it's starting from principles and leading to one answer. So if I write down all the assumptions, everyone in the world will derive the same posterior PDF. And the only thing that will be left is the different assumptions we made, which is exactly the case we want to be in science. So deriving your statistical procedure is something that we do all the time. And it's a little different from the way of thinking about data that happens elsewhere. Okay, right, so hopefully we're all on board with this, and things are getting simpler and closer to things that you recognize. So what we're now going to do is just go ahead and calculate the posterior PDF. I told you it was the answer, so we should calculate it. So for two-dimensional problems like this, M and B, we can just go ahead and calculate it on a grid. Everywhere in parameter space defined by the prior, we can compute the posterior. And we'll see why, hopefully you can see why in this expression up here, that both of these things on the right-hand side, the sampling distribution for y, this was the Gaussian suggestion. And then here is the prior for M and B, which were various suggestions of uniform priors and so on. So both of these are functions that we can evaluate at their parameters.
But there is an error then, because this sigma k is not going to be the error of the Gaussian.
No, so let me go ahead and fix this, because it is confusing, I agree. I'm going to delete this because I said I'd absorbed it into H1. So now maybe that looks better. Right, so just...
I think this is a very strange model, because you are assuming that X has all the information of Y, which is weird in any realistic.
Okay, so the question is, this model looks weird somehow, and maybe because in real life you're expecting there to be uncertainty on the x's as well.
On the model, yes.
So
not on the x, on the model, but the line or the x, your predictor is not going to have all the information on the y.
Right, okay, so in real life you expect there to be intrinsic scatter.
A trend of the model, and not like a straight
right,
line.
not just a straight line, but a fuzzy line, right, where the y true k's have some intrinsic dispersion. And so one of the hacks I'm going to suggest at the end of this is that you rework this to include intrinsic scatter. But this model may look weird, but it's actually used an awful lot in science. And in fact, you read it in astronomy papers all the time, where people either explicitly or implicitly neglect the possibility of intrinsic scatter. And they just go ahead and assume a clockwork universe where if you know X, then you can compute a true Y. And then all that you're left with is understanding the observational uncertainties. So this is not so weird. This is in the literature all over the place.
Yeah, I think that's actually a really interesting avenue of future research, is saying like, hey, wait a minute, maybe the color magnitude diagram isn't actually just a perfectly straight line, and that there's intrinsic scatter even in a globular cluster that's exactly the same age.
Right,
there's a lot of progress to be made.
Whoa.
Future direction.
Wait a minute.
Okay, so for the people on the outside, future directions of research suggested, which is to read a paper, see a straight line being fit, and then suggest intrinsic scatter. For example, in supernovae, are they really standard candles? Like, is their luminosity dictated by, some, or is there intrinsic scatter in the population of supernovae 1A? Someone could write a paper.
Intrinsic scatter is just uncertainty in the true model that's generating that. I mean, what? I mean, that's just uncertainty on our knowledge of H1.
Yes.
Okay,
What's
so
intrinsic scatter if it's not?
Okay, so
assuming a model.
Right. Okay. So there's a question coming up here. How would it work to include intrinsic scatter in here? So let's look at the PGM again. So in this PGM, we said, right, we draw M and B to simulate data, and then we go to this node here, and given xk as a constant, we can just go ahead and predict the true value of y, because we know the gradient m and we know the intercept b and we know the x value. So y equals mx plus b. And then the only thing left to take into account is the observational uncertainty. So if there was intrinsic scatter, this thing here would no longer be a dot. It would be a circle. Exactly. I see people making circle signs out there, which is to say that there would be some, you would have to, when you were simulating data, you would have to draw a yk true from a broad distribution that's not a delta function but is broad.
But that maps exactly onto a case that is a different H1.
Yes, exactly.
Now you still have a completely fully specified model.
Exactly.
And the model is M and B and then the intrinsic scatter.
Good.
There's no, I mean.
Okay, so Andrew is saying things that everyone in the room is agreeing with, which is that would correspond to a different model H2.
Right.
I'm just taking a hard line on what the interpretation of intrinsic scatter means. It's just
a different model. Intrinsic scatter implies a different model, but it's similar to the previous model. It has some elements in common, but it has this additional parameter.
It's exactly the same formalism.
Yeah, it's still probability theory.
Okay, extra parameter.
Okay, comment from Brendon on this.
I feel like we've just seen a special case of something that's happened to me a lot on the Astro Statistics Facebook group, which is that we're all really good at questioning the assumptions, which is really great. But there's also, like, questioning assumptions is over here, and calculating the result given those assumptions is over there. And once I got into a debate that was centered on the second project of what's the result given these assumptions, and yes, I know they're implausible, but I'm interested in the result conditional on these assumptions. And it got into a really long discussion because everyone wanted to question the assumptions. I just wanted to try and make clear those two different things.
Yeah.
And that's really is clear. So one of the things that I think is so important about this like paper template where you say, here are the assumptions, here's the result given those assumptions, here are the issues with the assumptions, is it clearly separates those two things. Because it's also the case that a lot of the complaints we get about in our papers is, your result is wrong. To which my answer is, all results are wrong. It's just that our results are correct given our assumptions.
Right, so there's a difference being drawn here in the room between results that are correct given assumptions compared to claims of wrongness because of the assumptions. So hopefully this framework is able to separate those things. Okay, so we should keep going a little bit. There's 15 minutes to lunch. I'm already thinking that we're going to have to continue this, Daniel, to tomorrow morning, I think. It might solve our problem of what to talk about on Friday morning. Okay. So, evaluating the posterior on a grid. I showed you that they were functions we can evaluate because we said Gaussian and uniform. And so let's just go ahead and do that. There was going to be an exercise here for you to do, but we've spent our time doing discussions instead. So here is a log likelihood function. You can see you have to provide x and y and sigma y constants, and you also have to provide parameters m and b. And then here you can see me calculating the likelihood term by term. So going through each yk, calculating the value of a Gaussian function and taking the product, and then at the end taking the log. This is the wrong way to code this up, but I wanted to show you it just because it looks like the math we just wrote down. Okay, if I'd been able to operate notebooks properly, this would have magically appeared as an answer, and you can see in NumPy you get this instead. So, the bottom line, the np.sum of this y minus mx plus b, that's the thing that I was calling w squared earlier. So it has reappeared from the...
By the wrong way, do you mean just the slower way, even though I know this is back all the way to day one?
Just slower, yeah. Actually, at one point I thought this wasn't going to work at all because of taking the log of a very small number. But it turned out that for this problem it did work.
Okay.
But in general, we work with log likelihoods from an earlier stage, right? So doing sums rather than products. Sums of log terms rather than log of big products, because of this numerical.
So in some cases, you might get the wrong answer with multiplying and doing a lot, right? The numbers are too small.
Yep.
That's exactly what he was saying.
Yeah, exactly. Wow, it's hard for me to be heard at the back. Hey.
Can you repeat that? I couldn't hear.
So Tina was pointing out the same thing that I was, which was sometimes if you code the likelihood as a product, which you then take the log of, you get wrong answers because of numerical overflow or underflow or something. So it's better to take the log of the terms and sum them than to take the product of the terms and log them. All right. So here's my prior function. Oh, I guess I need to execute these cells, otherwise nothing will work. So that one, and then immediately replace it with that one. And now here's my assignment for the log prior, which is not the prior on the log parameters, it's the log of the prior density. And so I'm doing uniform in M, uniform in B, where I specify some limits and pass them down into the function. So I just went ahead with the easiest thing to reflect my knowledge of the problem. Okay, so let me execute that. And now here's code to evaluate on a grid. I make a list of M parameters and a list of B parameters, and then start filling up element by element the log posterior. Really, I should have called this the log unnormalized posterior, because here you can see straight line log posterior core was just the sum of the log likelihood and the log prior. Okay, so let's go ahead and do that. Okay, so then I'm making a plot of that 2D array. There it is. All right, so that's the answer to our problem as I've defined it. And the X that you see, or the cross, that's the values that I calculated right at the beginning of this from the least squares fit. So you can see for this assignment of priors and for this choice of likelihood that we made, the two things agree. Yep, Tina.
For the section above about the straight line, you said it's not this, it's this. Can you say that again? I didn't understand you. The
unnormalized that you hadn't normalized.
Oh, yeah. Okay, so there's a question about, to clarify. Yeah, so you see straight line log posterior here is just the sum of two function outputs, straight line log likelihood and straight line log prior. So this is missing the normalization factor. So I really should have called this straight line log unnormalized posterior, just the sum of those two logs. And then when I evaluate it on the grid, I'm making the log posterior, that is the unnormalized posterior everywhere. And then you can see here, I'm not exactly normalizing it, but I'm making it plottable by subtracting off the maximum and then exponentiating. And so the thing that I'm plotting is the posterior, what I'm calling the posterior, not the log posterior. Okay? So there we are. So in abstracts, they don't let you put plots. So you have to come up with some other way of reporting in some easy to understand way what your inference is. And so a common thing to do is to do two more integrals. That's to marginalize over M and marginalize over B one by one, and compute the median of the 1D marginalized distributions for some central value. And then maybe the range that encloses 68% for historical reasons of the posterior probability. You compute that and report that as a credible interval.
Why is the B and the M so dependent? Have so much correlation between them?
Why do we see this degeneracy? Why do we see correlation between M and B? That's coming from the way I parameterize the straight line. So if instead of the intercept with the y-axis, we'd chosen something more sensible, then we'd see that angle change to something more horizontal or vertical.
And specifically, if you chose the intercept at the sort of middle of the data, that would be kind of the better.
Yeah. So if I'd been lucky and chosen the intercept to be you're right. If I'd chosen the intercept to be
the value of the intercept at x, median x, or
right at the middle value of the x range of the data, that would have been more stable. Yeah, that would have been a better choice.
So x minus mean x, for instance.
You're talking about the priors?
No, just if you go back to the model is y. If you can go back to the data, the model is y equals mx plus b. All the x's, though, are not around 0. They're all at a high value. So if instead you pick the model as y equals x minus mean of x times m plus b, then your intercept would be the measurement of the y value at around 175 or somewhere around there, rather than at 0, which it is right now. So by making it at 0, then the slope and the intercept, what the value is at 0, gets very correlated. If you pick near the middle, then the slope can be whatever it wants, but the middle value of the intercept is going to be independent of that slope, or close to independent of that. And so it would be much less slope.
And then your intercept would be the mean of y.
Right.
Well, kind of something related to the mean of y. Yeah, it would have an interpretation like that. The reason for using the parameterization I did might be because I understand my prior PDF in terms of the intercept with the y-axis. You can imagine a case where I think I know that from previous experience or from some theory or something.
There was a suggestion of putting the prior between 50 and something, so that would work. If I'd set the uniform prior to between 50 and 150. Or, imagine if you were further away from 0, for example, and you look at your data and you set the limits of the uniform prior for that intercept, which then at 0 is not within those limits. Does it make sense what I'm saying?
Are you asking what would have happened to the inference if we'd chosen a uniform range more like 50 to 150 instead of 0 to 200?
I think it was just reiterating your point, because I mean, we chose, let's say if you chose the uniform prior on B to be between 50 and 150, if you then suddenly defined what B meant and you moved it over to be the intercept at the middle x value, then you should also adjust your prior.
Exactly, yeah. If you change variables from the one that you were interested in at first to something new, you have to also transform your prior density or adopt a new one. But they're not going to be the same. So the prior PDF for the transformed parameter is not going to have the same functional form in general as the prior PDF for the untransformed parameter. So this is related to what Brendon was saying this morning about unintended consequences. You might assign a prior PDF on one parameter that then when you transform it to some function of that parameter gives you a prior PDF in that function that doesn't make sense to you. Okay, so let's keep going. We've now answered our problem, and as you can see on the right, well, we can't see on the right hand side, we're about a third of the way through. So let's see, where are we?
Before you go on, there's a question from Twitter.
Oh, cool.
And Paula Sarkis would like to know your or David Hogg's opinion, or both your opinion, on the correlation coefficient from a Bayesian point of view.
They want an opinion on the correlation coefficient from the Bayesian point of view.
The correlation coefficient is this thing where you have x's and y's.
So correlation coefficient is
you get some number.
Is a summary statistic that you compute from the x's and y's handed to you in a data file. And I guess the question is, how does that relate to the parameter in a Bayesian model? Maybe it's hard to tell from Twitter.
Maybe the question is also just, what do you think about it? Should you use it?
Should we use it?
It's the same model. It's just the reparameterized m based on, or given the variances of x's and y's. And then you get the correlation coefficient. So you can reparameterize this model.
So the answer from the floor was that it's the same model at heart, so a straight line going through a bunch of points. But the correlation coefficient is a summary that captures that slope, I guess, for the model.
But it's not obtained by least square fitting.
It's not obtained by least squares fitting. It's an operation you apply to the data. It's a summary statistic. And so
like, so you look at the ensemble average. If two variables x and y, the correlation coefficient is ensemble average of x and y divided by the square root of the variance each of those squares.
Right, so it's that particular summary statistic of the data.
And if they're perfectly correlated, then R the correlation coefficient is equal to 1.
Right.
It's still with squares because you're basically fitting by very quotient to the data.
Okay, so the interpretation of it is in terms of a model.
More like
it's a measure of how linearly related are both.
But it's a measure of how the data are correlated together.
Linearly related are.
Right.
So I think
equal to 1 or minus 1 if they are
right. Exactly. It's
exactly in a line.
a test statistic that summarizes the correlation properties of the data. So there's no model involved in computing correlation coefficient, but there's an interpretation of it, and you can relate the value of the correlation coefficient to the gradient you would infer under certain conditions. But if we were to have assigned a different prior PDF for the gradient and then inferred the gradient, it would not be simply related to the correlation coefficient, which is a summary statistic of the data. But that's okay, both things exist. The danger comes in interpreting correlation coefficients as shortcuts. You have to understand what assumptions are involved, and so that connection is interesting for unpacking assumptions that involve those statistics. Okay, so we've reached, by my watch, almost 12:30. In the rest of this notebook, we're going to move from doing this brute force calculation of posteriors on grids to something more practical and more efficient, which is sampling the PDF, as Brendon mentioned this morning. And then with those samples, do some checks of the model and start looking at the probability of the data given the model. But we're not going to get through all of it in the next 5 minutes. So we have to make a decision about how to use our time. Suggestions from the floor. Is lunch